Uh, It is my pleasure to introduce our guest speaker, Liu Ziyin, for today's seminar. He is a postdoc student from the University of Tokyo and working on deep learning. Today, he will share his insights and expertise on clasp and phase transition in deep learning. Please begin when you're ready.
Oh, thank you so much for the introduction. Just to correct, I'm actually a PhD student. So my name is Liu Ziyin. I'm from the University of Tokyo. Today, I will talk about collapse and phase transitions in deep learning. So this is the table of contents for this presentation. I will start with introducing the phenomenon of collapse in deep learning, and then I will introduce a landscape perspective of collapse, which is mainly based on my work. Lastly, I will talk about how collapses are related to symmetry breaking in deep learning. So let me start with defining collapse. Well, let X be the input data, and F a neural network, and f of X the relevant representation of a data point. And consider the covariance matrix of the representation, which is defined as G. A collapse happens when G is low rank. We will mainly be working with linear models, where F is defined as X times multiplied by a series of matrices. In this case, that G is low rank is the same as the model W1 times multiplied up to WD is low rank. So there are mainly three types of collapses people have noticed. First of all, you have neural collapse that mainly happens in supervised learning. You also have posterior collapse that mainly happens in Bayesian deep learning. And you have dimensional collapse, which mainly happens in self-supervised learning. While independently discovered, all collapses happen when the learned data representation becomes low rank. In this talk, I will use the word complete collapse to refer to the case where the learned representation becomes zero rank, and a partial collapse refers to the case where you are low rank, but you are not zero rank. So let me start with posterior collapse. In Bayesian deep learning, especially in the setting of variational autoencoders, posterior collapse happens when the learned posterior distribution becomes the same as the prior. And we will see that in case of linear models, this is equivalent to that the mean of latent variables is low rank. Chronologically speaking, this is also the earliest discovered example of collapse. And posterior collapse is mainly regarded as a bad thing that you want to avoid. Briefly speaking, what you do in Bayesian deep learning is that you often want to minimize this loss function, where it's it contains a likelihood term and a prior term. It's also common in practice to weight the prior term by a parameter beta. And collapse happens when beta is large. So here is what you get if you train a nonlinear but simple model on MNIST as you change the value of beta. So as you see that as you increase beta, the generated images becomes more and more blurred, and the variations sort of diminishes. And when you have a very large beta, you basically output the same constant every time. And this is the case of a complete collapse. What comes before are partial collapses. In supervised learning, a neural collapse happens when the data representations are the same as the class mean. Well, namely, it happens when the inner class variation vanishes. Neural collapse is commonly regarded as a good thing because it suggests that the model is only learning the task-relevant features. Well, here, often you minimize this loss function, which usually contains a classification term, which is, for example, a cross-entropy loss, and you have a regularization term. For example, a L2 regularization with a regularization strength gamma. So here are examples of posterior of neural collapse in case of supervised learning. I think here the authors are sort of plotting the representation, a 3D projected representation of the penultimate layer of ResNet. So at initialization, the cluster means, which are these sort of how do I say? These are the class means, and these are sort of individual data points. And you see that you have large variation across classes and across different data points. And this is what you get when you reach roughly zero training error, but you're not yet having zero training loss. So you have clusters, but still within each cluster, the data variations remains. Whereas if you train up to convergence, you see that the data variations actually vanishes. So this means that your representation has become low rank. Oh, so here is a animated generated by the original authors, showing how sort of this collapse happens as you train. So a question here is, why does the collapse not happen for a linear regressor? So here is sort of the standard solution to the rigid linear regressor problem. Here gamma is your L2 regularization. This is the feature covariance. And this is the expected value of x and y, which is roughly the signal term here. So here, as long as these matrices are full rank, your model will never become say low rank or zero rank. So this is a question to consider. Lastly, this is more recent. In self-supervised learning, people have discovered the phenomenon of dimensional collapse. The dimensional collapse here refers to the case when the learned representation becomes low rank. Sometimes it is regarded as a good thing, sometimes it is regarded as a bad thing. Here, the objective often contains two terms. The first is an attraction term, and the second is a repulsion term, which often features let's say, a hyperparameter alpha that controls the strength of this repulsion. Usually, it is the case that the attraction term encourages representations of similar data to be close. And the repulsion term encourages representations of dissimilar data to be distant. And alpha controls the relative trade-off between these two terms. And one example of alpha is the strength of data augmentation. So here is here what I plot is the singular values of the last layer of a self-supervised learning model as a function of the injected data augmentation strength, which is, in this case, it's a Gaussian noise with variance sigma squared. And as you can see that as you increase the data augmentation strength, the singular values of the last layer becomes zero. Here is another example where people found that increasing data augmentation strength leads to lower and lower rank in the linear projector, which is basically the last layer of the model. And they also found that having a lower rank actually leads to better performance. So this is one good example where the collapse actually helps you a lot in improving performance. So it's something that you actually want to understand. So in short, collapses happen everywhere in deep learning. And the question is that, is there a universal cause? So these examples often share two common features. First of all, we have a data-dependent term and an effective regularization term. And the natural hypothesis is that you have the competition between data learning and regularization effect leads to collapses. The second is that the models are often trained for very long and sometimes to convergence. And the natural hypothesis here is that the collapses are related to the properties of the stationary points of the training objective. So this is what we'll do in order to analyze the collapse phenomenon. Okay, so now we are into the second part of this presentation. Let me start with the first hypothesis. So basically, is the competition between feature learning and regularization sufficient to cause collapse? Well, the answer is no. Actually, as I already have mentioned, the minimal example would be a ridge linear regression problem where you try to find the weight W such that you minimize this loss function. And A0 is defined as the feature covariance. The stationary point for this problem is unique because the problem is convex. And as long as A0 is full rank, the model would be full rank and there is no collapse. So the lesson here is that we need either an advanced loss function or a deeper model to see the collapse phenomenon. So here is the example which shows the test accuracy of a few models on CIFAR-10. Here, the blue squares are the performance of a linear regressor. You see that as you increase the LT regularization strength, the performance of the model remains roughly unchanged. Well, it changes very slowly, but there is no drastic change. Whereas for a deeper linear model, which are the orange squares, and for a ResNet 18, you see very dramatic behavior as you change gamma. And this is a manifestation of collapse. So basically, you see that linear regression is very insensitive to regularization, whereas deeper models are in a way hypersensitive. So so the first hypothesis would be that depth actually plays a key role in causing the collapse. So here is a minimal example, which is basically a one hidden layer linear model. Here W is the first layer weight, and U is the second layer. So X is the input, Y is the label. Epsilons are noises in the model. And you also have the LT regularization term. To be general, I give sort of different regularization strengths to the two layers. Oh, so we are assuming, for simplicity, we're assuming that Y is one-dimensional and epsilons are independent random variables with unit mean and sigma squared variance. And for example, it could be due to the use of dropout. And two layers have different strengths of regularization. And our approach is to find the global minimum, W star and U star for this loss function, and see if you can identify any collapse phenomena here. It turns out that this model is actually solvable. So let B denote the norm of the model at the global minimum. And you can show that if we define T, lowercase t, as the difference between the, let's call it the data the signal strength and the regularization strength, and then at global minimum, the norm of the model would either be proportional to square root of t if t is positive, or it will be 0 if t is negative. So in this model, in this problem, your model is either rank 1 or rank 0. So here you have no collapse, and here you have a complete collapse. For physicists, there are actually some interesting messages here. The first would be that you can treat B, the norm of the model, as an order parameter. And also you have a second order phase transition here because of the square root of scaling. And also the point where the signal strength is equal to the regularization strength is the critical point here, where the phase transition happens. Oh, sorry for the title, it doesn't make sense. But you can show that the loss function can be reduced to a one-dimensional effective form that looks like this. So the y-axis is your effective loss, and B is your model norm. It's a signed version. So basically, we have incorporated a sign into it, but I will explain later. So if you have a strong regularization strength, the point where the norm of the model is 0 actually becomes the global minimum of the loss function. And if you have a stronger signal or a weaker regularization, you have this shape of effective loss. So you have two sort of identical global minimum away from 0. And the red line shows the sort of what happens at the critical point. Here, the global minimum is still 0, but it's very flat. The Hessian actually vanishes. So learning would be very slow there. Okay, so the lesson from this example is that complete collapse happens in a two-layer linear model precisely at this point. And this critical point is independent of the width or data dimension. It's also independent of the data covariance. And it's also independent of whether you have noise. Actually, recall that we have the noise variables epsilon in the model. Actually, them being there or not actually doesn't affect this collapse behavior. And the natural interpretation here is that a collapse happens due to the competition between the signal strength and the regularization. Okay, so that finishes our discussion about a two-layer linear net in supervised learning. Now we start talking about posterior collapse. Well, for Bayesian deep learning, the minimal model is a linear latent variable model. Here we assume the data generation process where we observe data X, which generates latent variable Z and which generate latent variable Y. And when Y is equal to X, what we have is an autoencoder. Here the loss function is this form. The first term is the likelihood, and the second term is a prior term that matches the distribution of the latent variable Z to a prior distribution PZ. And you also have a, let's say, the regularization term beta that controls this strength of prior matching behavior. In case of linear encoder and decoder, and also assume that the distributions are Gaussian, the loss function would take this form. Here, the important thing to note is that U is our decoder and W is our encoder. Also important parameters are eta dec, which is the assumed variance of observation of the decoder, and this eta inc is the assumed variance of the encoder of the prior distribution. So here, this model is also, let's say, analytically solvable, and you can find what the singular values lambda and theta of U and W respectively are at the global minimum. And also function like order parameters, and the phase transition is again second order. For example, you can show that lambda I, which is the singular value of u, would be proportional to this term when it's positive. Here, beta again is the regularization strength. Eta dec is the assumed variance of the decoder, which is a hyperparameter, and zeta I are the eigenvalues of this matrix. So again, like the supervised learning case, it's a metric of how strong the signal is in the data. And eta dec is the prior variance, as I explained. Okay, so here is what you get if you run some experiment. At left, I show the loss function as you increase beta. So you see that the training loss increases to a plateau and stops changing as you increase beta, whereas the reconstruction loss and the prior term changes differently, but sort of weirdly at the points where collapse actually happen, where the singular values becomes 0, denoted by the vertical dashed lines. And here directly plots the singular values. So here sigma I is 1 if both lambda I and theta I are 0. So you see that collapses do happen as you increase beta. The singular values of the decoder and encoder becomes 0 at sort of critical values of beta. So in this example, there are actually multiple number of collapses, and that's equal to the number of distinct zeta i's you have. Okay, so this is actually remember the example I gave at the beginning. It's actually the same problem as the same experiment as these ones, and basically here is what happens when you have sort of 5 remaining non-zero singular values, which is sort of roughly in this regime. Here is what happens when you have sort of 4 remaining singular values, and here is when you have a complete collapse. So that's what the model output when all of your singular values are 0. And also you can plot the effective landscape, not effective landscape, just loss function itself as we change the norm of the model. So what we do here is that we train a model on MNIST in the non-collapsed phase. So basically with a small beta. And what we do is that we rescale all the weights by A at different values of beta. And then I plot the loss function. So basically, when you have a small beta, you have a local minimum away from 0. But as you increase the strength of the prior of beta, you see that you have this type of say qualitative transitions in the loss function. Okay, so that finishes our discussion of the posterior collapse example. And now I will talk about dimensional collapse, which happens in self-supervised learning. So it happens that, well, it turns out that dimensional collapses are a little different in the sense that it doesn't really require depth. So even if you have a single layer here, we will still be seeing a collapse phenomenon. We will see why actually. So the most standard loss function for self-supervised learning is info-nice, which can be written in this form. So the way you compute this loss function is that you first sample a data point x hat, and then you add data augmentation epsilon, 2 different data augmentation noises, epsilon and epsilon prime, to generate x and x prime. to compute the first term of the loss function. So you see that what it does is that it encourages these two representations to be close. And then you sample different data, chi hat, and you apply another data augmentation to generate chi. And what this term does is to encourage the representation of x and chi to be different. So basically, as I explained, it encourages x and x prime to be similar, and it encourages x and chi to be dissimilar. The loss function is invariant to a simultaneous rotation of the learned representation. So note that, for example, if you basically rotate the representation f by any arbitrary rotation matrix R, the loss function remains unchanged. So there is a sort of inherent rotational symmetry in the loss function. And we will see that this plays a very important role in causing the dimensional collapse. So as before, what we will do is that we assume that we have a linear model, but here it's just one layer. You have one weight matrix W, and you expand the log exponential term to fourth order. So this term. This reminds us of the Landau theory. Also, you assume that the data is Gaussian. If that's true, you can show that the loss function can be reduced to this form. For a general second order coefficients matrix B and a fourth order coefficient matrix sigma. Here, B is usually a linear function of A0 and C, and sigma usually equals to A0 plus C. Recall that A0 is the feature variance. And here we define C as the noise covariance. Oh, I didn't have the expression. So C is basically epsilon times epsilon transpose, the expected value of epsilon times epsilon transpose. So it's the covariance matrix of the noise vector epsilon. And A0 is the covariance matrix of X. So as I emphasized, note that a crucial feature of this loss is that the odd order terms vanish. And I stress that almost all SSL loss functions can be reduced to this form because they all have this sort of inherent rotational symmetry. Well, the reason why we have this, let me maybe explain a little more. Why we have this rotational symmetry is because SSL is all about learning a good representation of the whole data set. And if you globally rotate all the data representation, you are basically having the same representation. So it makes sense to incorporate this sort of information into the loss function. And that's why all the SSL loss functions tend to be rotationally invariant. Oh, sorry. Oh, yeah, sorry, this is right. So again, this model, by this, I mean, this loss function is analytically solvable in many cases. And you can show that the square root of the eigenvalues of this symmetric matrix are the order parameters. And if we assume that the noise covariance is isotropic, then you can show that these eigenvalues of the learned weight matrices scale like this term. So AI are the eigenvalues of the data variance of A0. And sigma squared is the noise strength. So basically, the lambda i's would be proportional to the difference between feature variation and noise strength. And this figure basically shows what happens when you train a model. And the dashed lines shows the sort of the predictions of the theory, and we see that the collapses do happen at the theoretically predicted points. Also, I also note that the critical points, which are here, here, and here, 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 are rather smooth due to the divergence of relaxation times at the critical point. Actually, as I explained before, at the critical point, the second order term in the loss function actually vanishes, and the leading order term is fourth order, and that's why at these points, learning are actually very slow, and and we always have to stop at the finite time. That's why you see these sort of smoother transitions in reality. And you can also plot the effective landscape. Here, what we're plotting are for nonlinear models. So what we do here is that we train a two-layer nonlinear network to convergence in the non-collapsed phase. And then I plot the loss function sort of at 3 different values of data augmentation strength as I rescale the last layer of the model. And you can see that at a strong augmentation, which are the orange lines, the place where the model is identically 0 is the global minimum. And if you have a weak augmentation strength, you have 2 sort of identical global minimum here and there. Also, you see that this pattern is robust across 2 different models where you have the ReLU as activation or Tash as the activation. Okay, you can, let's do more plotting. So here, instead of rescaling the model sort of along one dimension, now let's sort of rescale the model in 2 dimensions. So basically what we do is that we still train the model to convergence, and we sort of, we rescale the 2 rows. Sorry, here the model, the representation is just 2D. So there are only 2 rows in the weight matrix of the last layer of the model. And we rescale these 2 rows independently by R1 and R2. These are the sort of the landscape plots you get at 3 different augmentation strengths. Here is what you get when you have a weak data augmentation. You have 4 identical local minimum, actually global minima, and you have 5 saddle points. As you increase the data augmentation strength, you see that this dimension actually collapsed first. So you only have 2 local minimum in the landscape. Here is what happens when you have a very strong data augmentation and you only have 1 global minimum right at the origin where all the parameters are 0. So that signals a complete collapse. This experiment you can also do on ResNets and on maybe advanced tasks such as CIFAR10. So again, what we do here is that we train a ResNet on CIFAR10, but we sort of take the last linear layer of the model and we either rescale the layer in 1D or in maybe 2D. And you see that you see sort of complete collapse and no collapse behavior. Here is a 2D plot where when you have a small data augmentation strength, there is no collapse. Here, when you have a sort of intermediate augmentation strength, you have a partial collapse in R2, but you still have non-trivial R1 value. Ultimately, when you have very strong data augmentation, the origin becomes the global minimum, and you have a complete collapse. Okay, so these demonstrate how collapse actually happen even in very advanced modern models. And a interesting, curious question would be, do we only have second order phase transitions? Well, the answer is also no. So let's sort of confine us to the problem of supervised learning. Recall that our two-layer linear model for supervised learning takes this form. Recall that W is the first layer and U is the second layer. And you can generalize it to multiple layers. And the loss function would take this form. So again, you have a regularization term, and you have sort of 1, 2, until you have d many multiple layers. And after each layer, you have a stochastic variable epsilon as before. And here D is the number, the capital D is the number of hidden layers. Well, it turns out that as long as capital D is larger than 1, meaning that you at least have 2 hidden layers, the effective landscape becomes qualitatively different. In our paper, we showed that the loss function can be written in this form. When you plot it, you actually see these figures. So the orange line is what happens when you have a large gamma, which is the L2 regularization strength. And the blue curve is what happens when you have a small gamma. So the qualitative so let's compare. The figure here is sort of the landscape you get when you only have 1 hidden layer. So notice that the crucial difference is that if you have deeper models, the origin is always a local minimum. Sometimes it's the global minimum, but other times it's just a local minimum. And learning would involve escaping from this local minimum. Okay, so here is a comment. So B equal to 0, meaning the model norm equal to 0, is always a local minimum for capital D larger than 1. Okay, so in physics terms, this is actually like a first order phase transition. Okay, okay, so this is what I say here. There's a first order phase transition whenever D is larger than 1. And also note that the order parameter B as a function of gamma, the hyperparameter, features a jump at a critical value of gamma. So here is sort of the critical value of gamma. Of course, you can sort of prove it in a rigorous way, but we will sort of skip that part. And it would be interesting to actually look at this problem in a actual phase transition framework. So here what we define is the Ehrenfest type phase transition. And in these models, we're only looking at the global minimum, and that's basically the same as considering a 0 temperature limit of the free energy. And in that case, the free energy is nothing but the global minimum value of the loss function. And we say that the nth order phase transition happens if the nth derivative of L as a function of gamma is discontinuous. And it turns out that in terms of linear models, actually you can prove the following 4 results. First of all, there is no 0th order phase transition for any finite depth. So basically that means that if you're always training up to the global minimum, the global minimum loss value will not jump as you change gamma. Okay, and also D equal to 0, which is the linear regression case, there is no phase transition, and D equal to 1 has a second order phase transition, and D larger than or equal to 2 has a first order phase transition. And these phase transitions directly manifest if you just look at the training loss at convergence at different values of gamma. So the blue squares shows what happens for a linear regression. You see that the loss function value changes continuously as you increase gamma. So there is no phase transition here. For the case where you have one hidden layer, d equal to 1, you see that the loss function value increases up to a plateau and stops changing. But notice that the derivative of this curve is continuous. So you have a second order phase transition. Here, L remains continuous, but that its derivative sort of is discontinuous at this point. And that's a first order phase transition. And again, I show the performance of models trained on CFR10 as you vary gamma, and you see that if you have a linear regressor, the performance is roughly unchanged. Whereas if you have a deeper model, the performance of the model actually jumps to 0. Well, I mean, I wouldn't say jump to 0, but like collapse to 0 at critical values of gamma. So those signal complete collapses. Okay, so that finishes our discussion of the landscape of the collapse problem. Now I will talk about what is the role of symmetry breaking for these problems. Okay, so symmetries in deep learning landscape. Let us consider a generic differentiable loss function L, which is a function of the weights for vector of parameters W. It is often the case that for a subset of parameters, a sign flip symmetry exists, meaning that for this subset of W, the loss function remains unchanged if you flip the sign of W. And this would imply that the local expansion of the loss function around W equal to 0 takes a special form. For example, this. So the crucial feature here is that the odd order terms would vanish because of the sign flip symmetry. And for these type of loss functions, what we would expect is a Landau type geometry where if you flip the sign, you get the same value in the loss. And usually you have local minimum around the origin and the saddle at the origin where W equal to 0. Okay. So here, let me stress the matrix H. It's the Hessian of this loss function, and it is the quantity that directly determines the geometry of this loss function. Usually in deep learning, it's the case that H can be decomposed into, say, A minus gamma times C, where A and C are both positive definite matrices and for a controllable parameter gamma. And usually it is the case that gamma is due to the use of regularization or injected noise in the data. And gamma thus determines the geometry of the loss function. So that tells us that if we only look at the second order term of the loss function around this expansion, we can already sort of gather a lot of information. For example, in the subspace, where this matrix has positive eigenvalues, W is encouraged to be non-zero, and learning will happen. In a subspace where this matrix has negative eigenvalues, W is encouraged to be 0, and you would expect a sort of a low rank structure in W. And for these landscapes, the singular values of W usually would scale in a square root fashion. Oh, sorry, I should have changed the notations here. But it would scale in the square root of fashion. And in physics terms, this is like a second order phase transition. And the singular values of W can be treated as order parameters. So in case of the collapses we studied, what are the actual symmetries? Well, for a deep linear network, the sign symmetry exists between different layers. So what it means is that if you have a two-layer model, if you change the sign of layer 1 and layer 2 simultaneously, the model remains unchanged. And this is why for a linear regressor, you don't have collapses because there is no symmetry. And for a VAE, a linear VAE, changing the sign of the encoder and decoder simultaneously, the loss function would remain unchanged. And for self-supervised learning, the loss function itself, as I have emphasized, is invariant to the change of the sign in the last layer. Okay, so that finishes the presentation of the main results in this seminar. I will summarize what I have said into the following messages. First, a collapse is a ubiquitous phenomenon in deep learning, and there might exist universal explanations for it. Second, landscape analysis around the origin can explain the landscape causes of the collapse phenomena. And therefore, the origin is actually a very special point in deep learning. Sorry. Thirdly, collapses can be understood in the form of phase transitions. And the norm of the model, singular values of the weight matrices are good candidates of order parameters. And lastly, existence of symmetry and a regularization term leads to such transitions, because both the symmetry and the regularization affects the Hessian of the loss function. And probably the underlying most important question that remains open is, can existence of collapses explain the success of deep learning? This is because collapse encourages low rankedness and sparsity, which are actually good candidates for explaining generalization. And it's interesting to see that these sort of, how do I say, they do lead to sort of phenomenon in deep learning that actually affect generalization behaviors. And also, can we use collapse to design better learning algorithms? And perhaps a more distant question would be, do biological brains collapse in a way or not? Okay, that finishes this presentation, and this presentation is based on the following works of mine. If you are looking for the Bayesian deep learning problem, you should look at this reference. If you're looking at the discussion of second order phase transition, the NFAS type phase transitions, you should take a look at this work. And this work of mine studies the self-supervised learning problem. Oh, this reference I didn't discuss at all. I shouldn't have put it here. Thank you very much for your attention.
Thank you for your nice talk. Now we move to question or comment session. Do you have any comments or questions? Shirai-san, どうぞ.
Oh, thank you for a great talk. Also, I have a question about zeroth order phase transition, maybe page 36.
Okay.
I never heard of it, so please explain it a bit more.
26. Maybe it's just here. So there is what I'm saying is that there is actually no zeroth order phase transitions, right? In physics, what would it mean to have a zeroth order phase transition? It basically means that your free energy has to jump, but that doesn't really happen, right?
Got it. Okay, no, I'm sorry.
So there, the proof is that there is also no zeroth order phase transition here.
Got it. I'm sorry. Yeah, I understood that. Thank you.
The implication is actually quite, in my opinion, interesting, right? It basically means that you shouldn't be observing any form of jump in your training loss in deep learning as you vary the say the augmentation strength. But actually, you do see a lot of that when you actually train models in deep learning. And if that actually happens, it basically means that you have sort of been trapped in a local minimum that's not global. So I think this is a very cool interpretation of that.
Okay. So can I ask a different question?
Oh, please.
So in this left figure, so the blue plot will increase nearly linear, and that will, how to say, be more than 0.2, and how to say, so not merge to other two the plots, and how to say, so that will be infinitely large. So I'm talking about d equals 0, and the blue plot will increase forever.
Oh, okay. So you're asking if I continue to increase gamma, what will happen to this curve, right?
That's right.
I think it would increase actually towards this plateau, but you only reach this plateau at infinity.
Got it.
Because if you increase gamma, your model would be closer and closer to 0, but you never reach it, right? Okay. If you reached it at a finite gamma, then you would actually be having a phase transition, but you're not reaching that point at finite gamma. So that would mean that you're converging to that point at infinite gamma, I think.
So bound about 0.2 something is given by the theory. So is that trivial one, or?
Yeah, it's basically the training loss you get when your model is 0, right? It's basically the expected value of y squared. If you get what I mean.
Got it. Okay. There is a maximum. Okay. Thank you.
Any question or comments? So can I ask a question? So
please.
You showed beta dependence of the singular values.
Oh, okay.
Yeah. So what's the dimension of the matrix you're considering? This figure shows which singular values. So there are many singular values, or U and W.
Oh, sorry. I actually, actually in this figure, I didn't really show the singular values. I'm showing the sigmas.
I see.
But the point is that sigma is 1 if and only if both lambda and theta are 0. So lambda is the singular value of the decoder, and theta is the singular value of W.
Yes. So there are many. So U and W are matrices. So you have singular values of the number of the dimension of the matrices. So this figure shows one singular values among them. or some averaged quantities. So this sigma equal 1 means that all singular values are equal to 0.
No. I think here what we are plotting, I think these are high dimensional matrices. I forgot what the dimension was, but what we are plotting here are sort of the 5 of the largest singular values.
I see.
So sigma 1 would correspond to the largest singular value, lambda 1 and theta 1 of U and W. And that's why it collapses the last, right? So yeah, I think.
I see. Thank you. Any question or comments? Shirai-san.
Oh, okay. If there are no questions, I want to ask again. So, you showed a figure about landscape of resonant 18 on cipher 10 with.
Here.
So I thought your analysis is basically based on linear theory, but so in this case you used actual deep neural network too. And so yeah, please, how to say, show me how do you do this analysis. So maybe you told us about R1 and R2, so you used that, how to say, equation or theories to illustrate this figure. So please explain the details of this analysis. Yeah.
So the idea is that so actually people have noticed, let me first comment that people actually have noticed in self-supervised learning that the last layer of the model is in a way very special. And actually many interesting phenomena do happen to it. And here what I'm plotting is what happens if you only rescale the last layer of the model.
Okay.
And this is the model that, this is the layer that directly links to the linear theories, right? Because the symmetries in the loss function directly reflects in the sign of this weight matrix, right? And you would expect that the theory can actually be directly applied to this layer.
Okay. Got it. So the last layer in that is linear. So okay, you can do the same thing. Got it.
So the difference would be that here you still have W as a linear model, but B would depend on the weights of the previous layers, right? So you still have the same thing, but B and sigma would involve non-trivial functions of the previous layers.
Okay. Yes. Yeah, thank you. I understood.
Any questions or comments? So, if no, we will close this.
Can I ask?
Please.
I'm sorry. So so in your talk, you said this transition is kind of resemble to the, I say, something found in statistical physics. But so what are the differences between, how to say, what we see in statistical physics and this problem?
That's actually a very good question.
Okay.
What would the differences be?
Or so you think this is the kind of the same, but you want to describe it as similar or close?
I think Well, here the correspondence is only at zero temperature. In statistical physics, that basically means that you are zero temperature, right? In deep learning, that would mean that you have to train with gradient descent, actually gradient flow. And you not only have to train with gradient flow, you actually have to make sure that you reach the global minimum, right? You have to be initialized in the global minimum value in order to see these phenomena. And what would differ the most, in my opinion, and in my guess, would be what happens at a finite temperature. For physics, at finite temperature, what you get is the Boltzmann distribution, the Gibbs distribution, and you only get that if you have a isotropic noise, right? A constant isotropic level of noise, which are thermal. But in deep learning, the noises that you actually get are usually not thermal, because the noises, the randomness in dynamics comes from mini batch sampling. And those noises are definitely not thermal. They are actually parameter dependent. Therefore, I think at a finite temperature regime, the phase transition behaviors would be vastly different from statistical physics. But if you don't consider temperature, I think they're in many ways similar, I think.
Oh, thank you. Okay, there are a lot of implications. How to say? Interesting. Thank you.
Thank you for the questions. Actually, if you have any remaining questions, feel free to actually email me.
Okay.
Yeah,
Thank you. Actually, I was reading your papers and very impressed.
Thank you.
Thank you very much.
Do you have any comments or questions? If no, we will close the seminar. Okay? Yeah. Thank you so much for your insightful presentations.
Thank you so much for inviting me to give the presentation.
So Takahashi-san of Kabashima-ken suggested you as a good speaker for this seminar.
I see. Maybe I should go say thank you to him when I go back to my office. Okay. Thank you very much.
Thank you very much. So I will close this room soon.
Bye-bye.
See you.